So in lesson number 2, which is part of our initial module here, we're going to talk about OSPF. All right? Just like we talked about with EIGRP, we have to be able to find a way to scale OSPF, and that ability to scale OSPF is going to depend on our network structure, addressing scheme, etc. So it's very critical in the case of OSPF that we have a hierarchical addressing environment, and a structured address assignment is really one of the most important factors, particularly with OSPF, in determining the scalability of the network that we're building inside of OSPF. So in this lesson, we're going to discuss the designing aspects or the design aspects of an advanced routing solution using OSPF, how to scale OSPF, and what factors are going to go into the ability to influence convergence in a medium-sized OSPF network as well as a very large-size OSPF network. So we'll talk about the different factors that influence OSPF scalability. We'll talk about the impact of adjacent neighbors on OSPF scalability, just like we talked about with EIGRP being 3,000 routers or 4,000 routers. We'll talk about routing information in the area or the domain. What is the total optimal number of routers in an OSPF area? What else will we talk about? The number of areas that an ABR can be part of, right? We kind of mentioned that a little bit in the first lesson. We were kind of talking about OSPF and EIGRP together because we didn't have the concept of hierarchical design in EIGRP. Obviously, these things are going to apply to OSPF. All right. What is the area design that I should be considering? What is the hierarchy of OSPF that I should be considering? Where do I apply domain summarization? What is the challenge that we face when we're dealing with OSPF in a full mesh design versus a hub and spoke design, right? What's the best place to place the ABRs in a hub and spoke environment? Does the ABR become the hub router, or do we place the ABR at the spoke side, right? We talked about that, Gaith, a little bit in the previous chapter. All right, what happens if I have a lot of areas in my hub and spoke environment? All right, and then we're going to also, of course, talk about the different network types. Remember, in OSPF, we don't just, unlike EIGRP and OSPF, we have lots of different network types, and OSPF handles those network types differently as far as automatic neighbor discovery goes, as far as the hello and dead intervals, and so on. All right. The other aspect of discussion is going to be how can I make sure that OSPF converges more quickly? How can I improve that convergence time and the convergence process? How is bidirectional forwarding detection applied to OSPF? Well, basically the same way it's applied to EIGRP. All right. What else will we talk about? I think that's about it. I mean, we're going to talk about event propagation and event processing and OSPF LSA flood reduction and database overload protection, but those are some of the kind of the final things that we'll talk about as we move through this particular module, the enterprise connectivity module. All right. All right. So when it comes to scaling OSPF, scaling is going to be determined based on the utilization of 3 different router resources: memory, your dynamic RAM, the CPU, and bandwidth on the interfaces. Okay? So in any regard, whether we're talking about prefixes, the number of connections, the stability of the network, it's always based on memory, CPU, and interface bandwidth. And these factors, this workload that OSPF imposes on those 3 components of the router depends on these factors that are listed on this slide. For example, the number of prefixes, right? The number of prefixes that OSPF carries is probably one of the most important factors regarding OSPF stability and scalability, is the number of prefixes. The stability of the connections is important as well. If we have flapping links, for example, the flapping links introduce recalculations into the routing process, which is going to increase the CPU cycles, possibly the interface bandwidth, because we're re-advertising DVDs, we're re-advertising LSAs, we're re-establishing neighbor adjacencies, and so on. The number of adjacent neighbors for any one router is important as well. We know that OSPF floods all of the link state changes to all the routers within an area. If I have a lot of neighbors, then I have a lot of information to disseminate when link state changes occur. All right. Now we'll see some of the limitations of OSPF with regard to how many neighbors we can actually have in our environment. The number of adjacent routers within an area is important as well. OSPF uses a very CPU-intensive algorithm. We know that. Dijkstra's algorithm, DIJK-STRAS, is a very CPU-intensive algorithm. The number of calculations that have to be performed is it's a logarithmic proportion to the number of packets, right? So let's say I have number n of link state packets, then the number of calculations is n log n, right? So the larger and more unstable a particular area is, the greater the likelihood of performance problems that are associated with different routing recalculations is going to occur in a particular area as well. All right? So it's not just simply, a linear extrapolation based on the number of links and the number of advertisements and so on. It's actually exponential, right? And the effects are exponential. Then lastly, we see listed here the number of areas supported by any one router. Any router that has to run the link state algorithm, it's going to have to run that link state algorithm for every link state change that occurs for every area that the router is a member of. All right? Now, that being said, that means that, as an example, an ABR, which is a member of at least two areas, the backbone area and then some other adjacent area, is going to be more affected by link state changes and having to run the link state algorithm. All right? All of this said, and all of these factors, which by the way are probably no surprise to you guys, because when we talk about OSPF in the CCNP class, we talk about these things, right? How many neighbors do you have? How many prefixes are you learning? How large is the database? How stable are the connections? And so on. All right? But the first and most important decision when you're designing an OSPF network is to determine which routers and links should be included in the backbone area and which routers and links should be included in the adjacent areas to the backbone. That's the most important aspect. All right? All right. And we'll get into that in more detail as we move through the chapter here. We may not see any lab demonstrations today, but possibly tomorrow I'll try to build some stuff in GNS3 that we can play with if we get a chance. I'd like to have some configurations as a backup here. This is not a configuration class, right? It's never been a configuration class. The CCDA is the same way, right? We talk about theory, we talk about concepts. We rely on the CCNA routing and switching and the CCNP routing and switching courses to get the actual configuration components. But anyway, all right. OSPF scalability is going to be influenced, number one, and we saw that as one of our items here, this one right here, the number of adjacent neighbors for any one router. So OSPF scalability is influenced by that number of adjacent routers or neighbors. Now neighbors can either be connected to the same segment, or each router can use its own connected segment to become a neighbor. We still have to establish those adjacencies based on directly connected relationships, right? Common subnet, common area, etc. In the case of a multi-access network, which we kind of see depicted here, this is considered a multi-access network, and this is considered a multi-access network. One of the things that occurs is that on each segment, in this case the left and the right, each segment has something called a designated router and a backup designated router that allows us to build adjacencies with all the other routers. What is the overall goal of the DR-BDR process in OSPF? Can anybody describe that to me? I mean, I'm going to describe it in a minute if you can't, but can anybody describe the overall goal of having a DR-BDR on a multi-access segment?
Just to elect a designated router to forward the multicast traffic, just to have a peer ring relationship with the BDR or the DR that will take care of the routing of messages and routes.
Right. And the goal of electing a chief, I call it electing the chief, even though it's not technically the term that's used, but I call it, the goal of electing a chief for a segment is to reduce the number of link state advertisements that have to be propagated on that segment, right? So let's say this guy's the DR, and to make it simple, let's just say that we don't have a BDR. I mean, we normally would, but let's just say, as an example, that we don't have a BDR. So this guy is going to form a full relationship with that router, and that router. If something changes on this router, that advertisement gets sent to the DR, and then the DR sends those updates to the other routers in the segment. What type of relationship do these two routers form? They're not fully adjacent with each other.
Yeah, they're two-way.
They're a two-way adjacency, right? They form a two-way adjacency with each other. In other words, they know that they exist. They know that they can become neighbors if they have to. In fact, they see each other in their neighbor list in the OSPF packets, hello packets that are being sent back and forth, but they don't actually exchange. They don't do the extort. They don't go through the extort state, the exchange state, or the loading state, or the full state. They maintain a two-way relationship. So all of the full adjacencies occur with the DR and the BDR. All right. That means that the fewer neighbors that exist on the segment, the smaller the number of adjacencies the DR and the BDR have to build. All right. Now, each OSPF adjacency represents another router. All right. And if I have another router in an OSPF segment that I have to communicate with, that means I have to exchange hellos with that router. I have to synchronize my link state database with that router. I have to reliably flood link state advertisement changes to those routers. And I have to advertise the router and the network LSA for that segment as well. Okay? Remember, there are several different LSA types that exist in OSPF. There's a Type 1 LSA, Type 2, Type 3, Type 4, Type 5, and Type 7. Those are the most common ones that we see. All right? Let's just do a quick review, because I know that they're not going to bring this up in this chapter in the slides. So let's talk about the different LSA types in general, talk about what they represent, who generates them, what the scope for those LSAs are. So a Type 1 LSA is called what? It's called a router LSA. All right? A router LSA is generated by whom? Who generates Type 1 LSAs?
The router in the area itself.
Every router does.
Mm-hmm.
Every router generates Type 1 LSAs. Okay? Now, I know what you mean, Gabe, when you say in the area itself, because Type 1 LSAs are intra-area, they're not inter-area. So Type 1 LSAs do not leave the area, not directly anyway, because they become Type 3 LSAs when they go through the ABR. Okay? So when we're trying to scale OSPF, when we talk about the design of OSPF and the scalability of OSPF, it is extremely important that you understand the impact that link state advertisements have on an area and the impact that they have outside of their area. Okay? Well, Type 1 LSAs don't really have an impact outside of their area because they're intra-area LSAs. They stay within the area. And they're represented in the routing table as an O. Right? Just simply an O route. Okay? What about Type 2 LSAs? Type 2 LSAs are called network LSAs. What do they represent? Interestingly enough, go ahead.
It's just a link for the, between the two routers within the area. It's not even passing the area, but it's for the, when you have a BDR and DR, so those are the kind of link state advertisement between them.
Yes, I'm going to add to that a little bit. You're on the right track. They are intra-area. First of all, they're intra-area LSAs, so they stay within the area. They actually don't even get converted. They stay within the area. They're never propagated to another area. But a Type 2 LSA doesn't actually even represent a network per se. It represents the network that the DR is responsible for. Okay? So Type 2 LSAs are generated by DRs and BDRs, and they describe the network that the DR is managing. So how many clients are connected to that network, who those clients are based on the router ID, what the prefix of the network is, and so on. So the goal of a Type 2 LSA is to simply describe the existence of a shared network segment and who's responsible for that network segment and who are members of that network segment. Okay? The next type of LSA that we see is a Type 3 LSA. Who generates Type 3 LSAs and what do Type 3 LSAs represent? Go ahead.
These are the ABRs that will be between the areas, inter-areas, routes.
Yep. Type 3 LSAs are summary LSAs. And a Type 3 LSA is generated by ABRs. And they represent Type 1s, basically. So Type 1s get converted to Type 3s as the routes leave the area. These are inter-area LSAs. They're represented in the routing table with an OIA, and they're generated by only one type of router, ABRs. They're not generated by ASBRs. They're not generated by internal routers. Type 3 LSAs are simply generated by ABRs. Now, by default, for every Type 1 LSA that might exist in an area, a type 3 LSA is going to get created, because summarization doesn't occur by default in OSPF. So if I have 1,000 type 1 LSAs, then I am going to see 1,000 type 3 LSAs that represent those type 1s. Obviously, the whole point of a summary LSA, though, is to represent a summary network. All right? And then we have type 4s, type 5s, type 7s. We don't want to go through every single one, but type 5s and type 7s are generated by ASBRs. They can be summaries or they can be non-summaries. They're going to be show up in the routing table as OE1 or OE2 or ON1 and ON2 routes. Type 5s are the E1s and the E2s, and type 7s are the N1s and the N2s. Both generated by an autonomous system boundary router that is redistributing routes from another routing process into OSPF. So type 5s and type 7s describe external networks that are being redistributed into OSPF. All right? Type 4s are generated by an ABR that has a ASBR attached to the area. So type 4 LSAs describe the ASBR, whereas the type 5s describe the external routes, right? If we get a chance to go into it in a little bit more detail later, we will, because obviously scalability in OSPF depends on your understanding, and your ability to scale OSPF depends on your understanding of these LSA types and who generates them, what they represent, and how you can control the propagation of those different LSA types. All right? Now, we can reduce the number of OSPF adjacencies with a hierarchical design. If we're doing load distribution, we can spread the branch connections to multiple hub routers if we want to. Volatility or the amount of change in other workloads need to be considered if we're determining how many peers the central hub router can support. And traditionally in the past, that's what we did with the DRs and the BDRs as well. We would try to influence the DR-BDR election process by changing priorities and router IDs, OSPF interface priorities and router IDs on OSPF routers to identify who's going to become the DR. But the problem with that concept, and this has always been the case with OSPF, the problem with that concept is that the election process is completely non-preemptive, right? That means that once the DR is elected, it stays the DR, even if somebody better comes along and has better values, better priority, lower priority, or a lower router ID. So in most cases today, we don't really concern ourselves with who the DR is or the BDR is for a particular segment, because most routers have the capability of supporting that function without any problem. All right? If you guys are involved in designing an OSPF network in the future, make sure you consider worst case scenarios, right? Restarts of routers, restarts of all the peers, flapping connections, whatever it might be, because that will influence your density of the routers in an area, the number of prefixes that you have in a particular area, and so on. All right? It's very difficult to give you a specific number because there are so many mitigating factors that go into designing OSPF, but you know, you kind of just consider your worst case scenario. Remember, the workload on the router also depends on how much routing information there is within the area itself and the whole routing domain. For example, if you're not doing summarization, and summarization does not occur in OSPF by default, so if you're not applying any summaries, then the density or the prefix density in your OSPF domain is across the entire OSPF domain, not just within the area. because every type 1 LSA that stays within the area is going to end up becoming a type 3 LSA. All right? All right. The other factors that are going to influence the scalability of routing information within an area and with the routing domain, the number of routers in an area, right? We talked about that previously. It's more likely than not that if you have more routers in an area, you're going to have more networks, more prefixes, more links, etc. The average number of links, the type of area. So this is important as well. The type of area is very important because we have in OSPF special area types. Total stub areas, totally stubby areas, not so stubby areas, and totally not so stubby areas. Not to mention the more common type, which is the backbone area and the non-backbone area. Hopefully we'll get into this discussion a little bit later. If it's not in the chapter, then I'll try to talk about it separately from the chapter. But special area types can greatly reduce the amount of overhead that OSPF sees in the network. Just like we have in EIGRP the capability of employing the use of stub routing and stub routing features, in OSPF we can do the same thing. The only difference is in OSPF the area becomes a stub as opposed to an individual router becoming a stub. All right? But we're already kind of seeing some of the similar concepts with OSPF that we saw with the EIGRP. Summarization, the number of external routes, the number of links, the number of neighbors, all of these things influence the overall scalability and stability of OSPF. Now, what does the number of routers have to do with it? Well, the number of routers and the links to adjacent routers within the area are going to determine how much information is in the link state advertisement database or how much routing information is in the area itself. The type of area, the amount of summarization, all of these are factors that's going to influence the amount of routing information that gets propagated through OSPF. The number of areas, the types of areas, that are configured on a router, particularly if it's an ABR, right, influence how much routing information gets sent throughout the entire domain. We obviously have different techniques and tools in EIGRP to reduce this information. In OSPF, we have very similar tools. Stub and totally stubby areas import less information about destinations outside the routing domain or the area than maybe, say, a normal area might. So using the stub or totally stubby areas reduces the workload of an OSPF router. Inter-area routes, which are summary routes, and costs that are advertised into an area by each ABR provide information about links in other areas. But if you say, for example, configure an area as totally stubby, not only do external routes, type 5s or type 7s get, well, type 5s specifically, not only do the type 5 routes get filtered out of the area, but a totally stubby area, the type 3s are filtered out of the area as well. So how do I route outside of a totally stubby area? What do I have to use to be able to route outside of a totally stubby area? How about a default route? Right? We're going to use a default route to route outside of a totally stubby area. Does that make sense? All right. Another technique to reduce the number of prefixes that are exchanged between areas is what we call inter-area filtering using prefix lists. Now, we don't have to use prefix lists. We can use access lists with route maps and and apply route filters to neighbor relationships and so on. But why do we typically use a prefix list? What is the benefit of using a prefix list as an example over an access list?
You can use them with the route maps, but I guess we can do both. But mainly for matching up some specific addresses and direct the direction with route map using prefix lists.
Right. Well, we can do that with an access list, but the benefit of using a prefix list is that we can match on prefix length as well as network information. So with an access list, you're only going to be able to match on IP address information in the route. Whereas in a prefix list, you can match on IP address information of the route, but you can also match on subnet mask length and how long a subnet mask is. So that's useful. If the book doesn't, if the lessons don't go into the use of prefix lists later, I'll try to give you guys time permitting, give you guys a little bit of a crash course on prefix lists. All right? Even though it is covered in the CCNP. All right? Another type of design element that we can incorporate is something called an ASBR, an Autonomous System Boundary Router. All right? One way to think about an ASBR in OSPF is that each router, each ASBR is in effect providing distance vector-like lists of destination and costs, right? Because these are external routes that are being injected into my OSPF routing domain. So you can kind of think that the more external prefixes there are, and the more ASBRs there are, the higher workload for Type 5 and Type 7 LSAs there will be, right? Now, we can use special area types like totally stubby or totally not so stubby to limit the scope of those external routes and to keep those routes from being flooded within an area. But again, that's part of your design consideration. I mean, the ultimate conclusion is that the area size, the layout design, the area types, the route types, whether you're doing redistribution or not, summarization, all of these things are going to affect the size of your link state database within a particular area. So there are some specific guidelines that are recommended, particularly when it comes to OSPF. Number one, keep it simple, right? Try to keep your routing databases as simple as possible. Use default routes wherever possible. Use larger aggregate summaries wherever possible, and so on. All right. The other is to keep it stubby or totally stubby, either one. If it's at all possible, the stub feature should be implemented whenever possible. All right. Because that's going to limit the size of, and the effect of database or topology changes, but it'll limit the size of your topologies and your databases significantly. Okay? All right. Another scalability factor that we have to consider with OSPF is the number of adjacent neighbors. All right? In fact, I would say, and I think most people would agree, that the number of adjacent neighbors is far more impactful than the total number of routers in an area, particularly on a particular router, right? The most important consideration is the amount of information that has to be flooded within the area. All right, sounds fair. If I have a network that has, I don't know, maybe 200 WAN routers and one fast Ethernet subnet in one area, another area might, or another network might have fewer routers or more subnets, which would make it less efficient. All right. The amount of information in the link state advertisement, which is how OSPF routers exchange their information, is going to increase with the size of the link state advertisement itself. Now, our goal to reduce the need for packet fragmentation and reassembly and so on is to keep the OSPF router LSAs under whatever the IP MTU size is. Because when the MTU size gets exceeded because the database or the information is too large, then that's going to result in IP fragmentation, which is a far less efficient way to transmit information. It's going to require more CPU cycles, it's going to require more memory, it's going to require more route processing, and so on. Also, if a router is generating a large number of LSAs, then you say, well, those LSAs would only be generated one time, but actually that's not true. In OSPF, we have something called a paranoid update, which means that every 30 minutes, the link state advertisement information is flooded out the entire network. All right? If you see a large number of LSAs, that might be normal. That might just indicate that you have many interfaces, maybe lots of neighbors. But it could also be an indirect indication that the area may have become too large, or maybe you have some flapping links and so on. Stability and redundancy. Stability and redundancy, most important criteria for the backbone. Now, we can ensure stability in the backbone, in other words, increase the ability for stability, by keeping the size of the backbone relatively small, or at least reasonable, compared to the rest of the OSPF network. And it's a balancing act, right? If the link quality is high, but the number of routes is small, then you can increase the number of routers. Redundancy is important in the backbone so that we prevent partitioning of the backbone whenever a link fails. We do not want to have a discontiguous area 0. So good backbones are designed that a single link failure doesn't cause this bifurcation of our backbone area. Now, the general rule of thumb, this course was published in 2015, so this number may have changed, but the general rule of thumb is that you should have no more than 300 routers in an area. Okay? Now, it's very, very difficult to specify a maximum number because of all of the mitigating factors that go into calculating that value, and because of all the design considerations that you have with regard to areas. But the number, well, let's say for test purposes, is 300. All right. Ideally, though, you want to monitor your OSPF implementation. You want to monitor your OSPF design. If you start to see issues, then you might consider scaling back the size of your areas to promote more stability. Welcome back. So ABRs, area border routers, we can see one depicted in the diagram right here. An ABR is going to keep a copy of a database for all the areas that they service. If the router is connected to 10 areas, it's going to have a list of 10 different databases. The number of areas per ABR also depends on a lot of different factors. Now, we talked about this a little bit before the break, about, a general recommendation, but it just depends. It depends on the type of areas that are connected to that ABR, how much CPU power the ABR has, the number of routes in the area, the number of external routers in the area, how many ASBRs might exist, and so on. All right. Whenever possible, you should try not to overload an ABR and spread the areas over several different routers going into the backbone. But, excuse me, typical designs only require usually a few routers to serve as your multi-area ABR. And these routers can then be upgraded to the latest hardware. And that being said, can support 50 or more areas per ABR. All right. Placing an ABR in tens of areas simultaneously is no longer an issue for modern routers. Traditionally, in the past, we said, okay, let's maintain this number of areas on an ABR. That number was usually less than 5. But it's not so much of a concern today. All right. In a lot of cases as well, even lower performance can be tolerated, meaning that a specific number of areas per ABR can't be recommended. It just depends on so many different factors. I generally tell my engineers, and I recommend to customers as well, monitor the ABRs. Add an extra ABR if you start to see degraded issues or performance problems on the ABR, so that you can distribute that load across multiple ABRs if it's necessary. All right? There really just is no specific recommendation because of all the different mitigating factors that might exist. Area design can also be used to reduce the routing information within the area. All right? Area design requires you consider the topology of the network, the addressing of the network, and so on. We can see from the bullet points here, match-up address summarization and areas as much as possible. Right? Just like we saw with EIGRP, the network topology, the IP addressing should be designed with the division of areas in mind. In EIGRP, we know that we can tolerate more of an arbitrary network design because we don't have a clear hierarchy of the EIGRP domain. We can apply summarization at just about any point in the network and at several points, but OSPF requires a much cleaner hierarchy. All right? You have to have a clear distinction of where areas exist and where they don't exist, where the backbone exists, where it doesn't exist, and so on. You can do this by geographic and functional boundaries, and a lot of companies do. They choose to use geographic and functional boundaries to design their area separation, but it doesn't always have to fit within a geographic or a functional boundary. The most important design element when you're implementing multi-area OSPF is to minimize the routing information that gets advertised into and out of particular areas. Right? Because remember, whatever exists in one link state database for one router within the area has to be propagated to all of the other routers in that same area. Changes need to be propagated, updates need to be propagated, and this is going to take up bandwidth, it's going to take up CPUs, and it's going to require the use, or it's going to require, well, quite a bit of use in the area, depending on the density of the area. All right. if we're seeing a lot of rapid changes, a lot of flapping interfaces and so on, those are going to require the most effort because we have to repeatedly propagate those changes. We can eliminate the effect of that, or at least mitigate the effect of that by using totally stubby areas, summary routes, because those special area types and summary routes reduce the size of our link state database, but they also insulate an area from external changes, right? Especially if it's implemented correctly. All right? Be very, very conservative about adding routers to your backbone area. Too many routers in the backbone area can definitely have a wide-reaching impact on your overall OSPF design. So, as a general rule of practice, you only put essential backbone routers into the backbone area, into area 0. All right? Everything else you keep outside of that area. In OSPF, we have a hierarchy just like we do with the EIGRP. In OSPF, we're typically dealing with a 3-layer hierarchy, core, distribution, and access. But OSPF allows, in what we saw in EIGRP, I mean to say, is the core, the distribution, and the access. But OSPF only allows for 2 levels. And those levels are the backbone area, area 0, and everything else that's connected to the backbone with an ABR. All right? Now you can see here that we have this 2-layer or 3-layer design. In a 2-layer design, which is the top one here, we have area 0 is the core of my network, and area 1, 2, or N, that's my distribution layer. Or I can say, okay, area 0 is my distribution layer, and area 1, 2, and N are my access layer. In either case, we're still dealing with a 2-layer model. All right? OSPF naturally is going to fit in either one of these design models, right? It just depends, where that design model is depends on the overall architecture, but we're still limited to this 2 layers, whether you call them the distribution and access or you call them the core and the distribution, doesn't really matter. All right? All right. I'm trying to think if there's anything else I want to say about that specific topic. Yeah, there might be. I'll probably bring up a few other points when we talk about some of the other scalability factors in OSPF a little bit later on. All right? If you need that 3rd layer of hierarchy, by the way, what do we typically see used to provide that 3rd layer of hierarchy? Some sort of EGP, like BGP. All right? The challenge that we run into, and a difficult question in OSPF design that we see, and Gaith was mentioning this earlier, is where do I put my ABRs? Do I put them in the core, or do I put them in the distribution layer? My recommendation, and I think Cisco's recommendation as well, is to have a general design to separate the complexity from the complexity. Meaning, you put the complex parts of the network into different areas. Now, part of the network might be considered complex when it has lots of routing information. Maybe it's a full mesh network or a large hub and spoke environment, or you have some sort of highly redundant topology, like a redundant campus or a data center. So that would be something that would go into a separate area. All right? Cisco defines that as separating complexity from complexity. Don't try to commingle too many complexities together, in other words. Summarize as much as possible to maintain the reliable and scalable OSPF design. ABRs, we know, provide opportunities to support route summarization or to create these special area types like stub areas or totally stubby areas. But in order to be able to facilitate that design, you have to have a structured IP addressing scheme to align those IP addresses with the areas so that you can have very efficient and effective route summarization. Now, the simplest way to do this, if you have the ability to design your OSPF network from scratch and implement it from scratch, is to allocate addresses into OSPF and assign separate network numbers for each area. That way you're guaranteed to have the ability to perform summarization on those ABRs between the areas. All right. Another thing to consider in a totally stubby area, and if you guys remember, totally stubby areas don't allow any routes in. You can't have an ASBR attached to a totally stubby area. You can't have type 7 routes in a totally stubby area. You will not see type 5 routes or even type 3s. The only thing that's allowed into a totally stubby area is a default route. Now you can have multiple ABRs in a totally stubby area. And in a totally stubby area, we can't really distinguish one ABR from another in terms of the best route to destinations outside of the area, because we don't have specific routes representing specific prefixes. All right? But it shouldn't really matter unless the ABRs are really, really far apart, geographically dispersed. It shouldn't matter much, right? The same can be said for stub areas. If I have a stub area, it's not going to be able to distinguish between ABRs for destinations that are external. For summaries, we can, because the summaries are allowed in stub areas. But for external routes, I can't really distinguish the difference, again, unless those ABRs are geographically far apart. It really shouldn't matter. So we don't have to really concern ourselves with it too much. All right? Now, OSPF Version 2, which is the original version of OSPF, was developed in the 90s, early 90s, maybe late 80s. I'm thinking now 1988, but around that time frame. Let's give it a window, 88 to 92. Okay? And that's OSPF Version 2 is OSPF for IPv4. OSPF v3, which is OSPF for IPv6, they're implemented as completely independent protocols. Which means that how you decide to implement your ABR design, what types of areas you make special and what types of areas are not special, it's going to be entirely different for each protocol stack. Generally speaking, I would say that most people that are running a dual stack environment, though, are going to, even though we can physically separate those design elements, we typically will align the area structure and the ABRs for both protocols so that we have an easier network to troubleshoot, maybe a less complex operationally, a less complex network, and so on. All right.
You have food there?
We have food every day at lunch, yeah.
What? I thought it was just like chips.
No, we have a hot lunch now.
Ah, jeez.
I know. Although,
well, I mean, I could go out and been there, but okay.
I know you're always good for food. I know that. Today we had pulled pork and baked beans and.
Well, either Wednesday.
right.
Sounds very southern, Scott.
Yes, it was a very southern lunch today. Tomorrow it'll probably be pasta or chicken or something. And they got a full bar here, Aaron, too. Just saying.
You know I don't drink.
I know. Even with an infant? Come on.
Right, yeah, now I will be.
Yeah. So, all right. There are many, many different ways to summarize routes in OSPF, although I will say it's not quite as flexible as what we see with EIGRP. All right. The effectiveness of route summarization depends on the effectiveness of your addressing scheme. All right. There are only two types of routers that you can summarize on, ABRs or ASBRs. And you can see here, if I have an ASBR, for example, here's an ASBR that is injecting BGP routes into Area 0. Actually, this is the ASBR here. Those are being sent in as Type 5s. Now, Type 5 routes are OE1 or OE2 routes, and they are sent through the autonomous system as Type 5s. They do not get converted to Type 3s. They do not get converted to Type, anything. They stay Type 5s, okay? Unless you have any kind of stub area, right? Type 5 routes are not allowed. Type 5 routes are not allowed into special area types, okay? All right. Now, if I have a special area type, and we see that here, this not so stubby area, I have an ASBR here. It's going to take those external routes. It's going to send them in as Type 7s. Type 7 routes are injected into OSPF using, pretty much the same process that we saw with the Type 5s. We have redistribution on the router, but when those Type 7s hit the ABR, they're going to get converted to Type 5s into the backbone and into all of my other area types that are not special areas. What we see here is the ability to provide summary address filtering, default information originate, etc. on these area autonomous system boundary routers, okay? And we can do area filtering and area range commands on my internal routers, right? Area range is what I use. Summary address is what I use on my ASBRs to create these summaries. Area range is what I use on my ABRs to create the summaries. All right? So Cisco has added an additional feature called area filtering, which allows us to filter what types of routes get sent into an OSPF area. And then we can use the RFC standards for OSPF, the IETF standards for area range and summary address. What's the goal? The goal is to minimize route information that gets inserted into an area. All right? Now, when you're doing this, there are a few guidelines that you should plan on in your OSPF network. Number one, configure the network addressing scheme so that the range of subnets that get assigned within an area is contiguous. That's a very important concept. Now, oftentimes we don't have that capability, right? We're limited to that. We're limited in that, I should say, because the OSPF networks tend to kind of grow on their own, I guess, for lack of a better term, right? You start off with a basic OSPF design, and over time, these networks kind of become their own living, breathing things, and they grow on their own. So we can't always assure that first bullet point that I just mentioned, which is to make sure that we have contiguous address space. All right. In addition, create address space that will split areas easily. All right. So assign subnets according to simple octet boundaries, /16, /24, /8, whatever. All right. Make sure you plan ahead for the addition of new routes into your OSPF network as well, so that as the network grows, you can maintain the first two principles, right? Meaning that we're inserting appropriate routes into the appropriate areas, the backbones, the border routers, etc. And what you're seeing on the diagram are some of the ways to summarize those routes to reduce the LSA database size and the flooding of routes inside of OSPF. We can use the area range command per the OSPF RFCs, the request for comments. Remember, OSPF is an IETF standard. Area range would be used on the area border routers between areas to facilitate this summarization. Okay? Use area filtering concepts. Area filtering allows us to identify, well, it's kind of like applying filters to neighbor relationships, because that's essentially what we're doing, but in this case, we're filtering between areas. And maybe tomorrow I'll show you guys a lab exercise where we kind of look at some of these principles. Summary address filtering. Maybe you don't want summary addresses to go through every single destination, right? So there's a way to apply summary address filtering as well. Originating default routes whenever possible. What is the benefit of originating a default route? Any ideas? Well, if I'm injecting default routes, what am I not having to inject? I don't have to inject regular routes. I can simply rely on those default routes to facilitate my communication process. All right? And then also filtering for my not-so-stubby areas, my not-so-stubby routes, and so on. Many, many different techniques that are available. I would say more than EIGRP, because in EIGRP we really only have two things we can do. We can do summarization, and we can do some sort of stub routing feature. Even though it's the same concepts in OSPF, there are some more granular approaches to applying those concepts in OSPF. We also have full and partial mesh topologies that we can implement with OSPF as well. When you're dealing with full and partial mesh topologies, obviously things get a little bit more complex. We typically implement these designs in networks that demand maybe high throughput, optimal routing, and so on. So where would we typically see full and partial mesh topologies deployed? Well, most likely in the core, right? In the core of our network. When you're dealing with a full mesh topology, though, when you're dealing with a full mesh topology, one of the things that you have to consider is the growth potential. Is the growth ratio, I guess we should say, of the mesh network itself, right? It's quadratic growth, meaning it's not a linear formula. All right? Full mesh networks experience this quadratic growth of interconnecting links each time you add a router. So there's a very, very difficult scaling factor that has to be addressed when you're using a full mesh topology. Something to definitely think about, right? It's not that I'm adding a single link for every neighbor. I'm adding exponentially more links for each neighbor that I introduce into the topology or into the design. Does that make sense? All right. So you look at the chart on the slide here, and you say, okay, yeah, two routers. Two routers is going to mean that we have one link to connect the two routers, but you add 6 routers, and instead of having 6 links, we actually have 15 links. All right? Just something to consider. And that number will continue to grow exponentially as you add more and more neighbors and more links into the network. All right? Flooding is also a concern, of course, as well. You guys remember the quadratic formula? Let me see if I can write it down here. To calculate the number of routers. So n minus 1 divided by 2. I didn't write that very well. Let me try that again. N minus 1 divided by 2. There we go. Oops. All right, so that's the quadratic formula. And n, of course, is the number of routers. So that's where if you plug in 6 routers, you're going to get 15 different links. Plug in 8 routers, 10 routers, whatever, it's going to grow exponentially. All right. All right. Flooding routing information through the full mesh is a big concern as well, because we always exchange routing information with our neighbors. Each router receives at least one copy of new information from the other routers in the network. All right. If I have a very large full mesh or partial mesh of OSPF networks, we have to deploy techniques in those networks to reduce the amount of routing information and flooding that's going to occur in the network. Again, hopefully, maybe tomorrow, I don't know if we'll get to it tomorrow, but by Wednesday for sure, I'll try to have some kind of pre-built exercises in GNS3 that we can apply some of these principles to and take a look at some of these different scenarios. All right? Now in ISIS, which we may not get to in this class, but in ISIS, there is a mechanism to counter this full mesh flooding. It is a concept in ISIS called mesh groups. But unfortunately, mesh groups are not available for OSPF. So we can't limit the effective flooding in OSPF using mesh groups like we would see with ISIS. We can simulate that process, and we simulate that process by using manual database filtering configurations. All right. So say, for example, we pick a subset of 2 or more routers in a mesh network that are going to flood the LSAs to all the other routers. We configure all the other routers to filter out their LSA advertisements for all but the subset of routers that we've decided to act as the, it's almost like doing a DR, BDR type of election, but we're doing it manually, if that makes sense. Okay? All right. Let's see, what else do I want to say about this slide? If I decide to do that manual database filter configuration, it's very similar to saying that we're doing the DR behavior, right, in a shared LAN. The only downside to doing database filtering is it is a manual technique. So you may end up blocking LSAs that you didn't want to block if you don't implement it correctly. All right? Now, another technique that we're going to talk about, which is part of the IATF standard, RFC 41, I believe it's RFC 4136, it's called OSPF flood reduction. Flood reduction eliminates the periodic refresh of unchanged LSAs. If you guys remember in the previous section, I mentioned that there is a concept in OSPF called a paranoid update, where we're flooding out OSPF database information every 30 minutes, right? Even if nothing has changed. That's called the paranoid update. All right, so we can turn that quote unquote feature off and get rid of that flooding behavior. All right. We'll see an example of that a little bit later on as well. In an OSPF hub and spoke design, any change at one spoke site gets passed up the link to the hub and then gets replicated to each of the other spoke sites. Makes sense, right? That's what happens in EIGRP. That's what's going to happen in OSPF as well. All right. The downside to this approach is that we're going to place a very significant burden on the hub router. And flooding, particularly flooding related to changes in the topology, is going to cause a significant amount of load on that hub router. So stub areas, just like we saw with the EIGRP, stub areas minimize the amount of information within the area, and by implementing these stub area configurations, we can eliminate the propagation of those LSAs and simply rely on default routes to route from one area to the other. All right. Now, a stub area or not so stubby area, I'll explain the difference of the two in a minute here, but a stub area is an area that allows summary routes to be inserted, but does not allow external routes to be inserted. And a totally stubby area doesn't allow anything to be inserted. A not so stubby area doesn't allow anything to be inserted except for summary LSAs, but the difference between a not so stubby area and a stub area is that a not so stubby area allows us to have an ASBR. So we're going to see type 7 LSAs injected into the not so stubby area, and then those type 7s will become type 5s when they leave the area. All right? I would say out of anything that you become familiar with, out of anything that you decide to become an expert with regard to OSPF design, specific to scalability, specific to resiliency and redundancy, is make sure that you're extremely familiar with the different area types and the effect of those area types have on the effect that those area types have on your LSA propagation. All right? Totally stubby areas, if you can implement them, are better than stub areas because, hey, if I can route with a default route, why not? Right? If I only have one ABR in an area, why do I need to inject any routes into that area? Why can't I just simply rely on a default route, use the type 1s to communicate within the area, and then use a default route to leave the area? All right? If the spoke site has to redistribute routes into the OSPF domain, make it not so stubby. But again, if you have the ability to make an area not so stubby, decide whether or not you have the ability to make the area totally stubby, or totally not so stubby, I should say in this case. All right. Another design concept would be to identify how many spoke routers belong to a specific area. Now, if I limit the number of spoke routers per area, that's going to reduce the amount of LSAs being flooded to the hub. But the problem with smaller areas is it allows for less summarization into the backbone, because each spoke router basically has a sub-interface on the hub router, and we're isolating smaller types of networks on each spoke router. It's a balance, right? It's a balance between what is usable and what is optimal with regard to how we distribute routes. Typically in a hub and spoke topology, we have a single or redundant hub and spoke connection. Maybe we have one, or maybe we have multiple hubs as our go-through points into the corporate backbone. And I like this. Many other network engineers also like to use distance vector protocols like EIGRP or RIP in hub and spoke networks, because they provide natural topology hiding behind the hub, meaning that they're really not. There is no dependence on the design or placement of the routers like where we place the ABR. Let's take a look at a couple of scenarios here and kind of compare and contrast the difference between these scenarios. All right, we know that we typically deploy hub and spoke topologies in a situation where we have multiple branch offices that are connected to the headquarters. That's pretty typical. And connections between the hub and spoke are typically WAN connections, right? Some sort of slow-speed serial connection or WAN connection. And those WAN connections tend to be, well, less reliable than our LAN connections, our fast Ethernet, gigabit Ethernet, 10 gig Ethernet connections. All right? So the WAN is really a common source of routing changes and topology changes that actually have to be propagated throughout the network. So the backbone, obviously in OSPF, very, very important. Typical design approach, well, keep area 0 small. We want area 0 to be small and stable. We don't want changes in area 0 constantly. All right, so to prevent WAN link flapping from affecting the core stability, we would typically use a hub router as the ABR between the core, which is area 0, and our spoke areas. Now, because this core router is the hub, as well as the ABR for all of the other areas, we may need to have a higher end router here because we're servicing multiple areas, our databases are much more significant, and so on.
Hey, Scott?
Yes, sir.
So that's what I meant when I was talking about the buildings and OSPF, and whether to have these routers in those areas as spokes or have them in area 0.
Right. The diagram on the right would be more preferred if the links that you're using are reliable and stable. The diagram on the left would be more preferred if the links that you're using are likely to flap or less stable. And it has to do with the number of changes that we would see in area 0. Obviously, if these links are going up and down constantly, area 0 is never going to converge. It's going to be constantly changing. In this case, though, if the links go up and down, we're not actually affecting area 0. We're simply affecting the non-backbone areas. Does that make sense? We want the core to be as stable and as solid as possible. All right? If you have reliable WAN links, if you have a small core, the design on the right is suitable. If you see a lot of flapping or you see issues with the WAN links, then the design on the left is probably more preferred. Make sense? All right. As the number of remote sites goes up, as we start to add more and more remote sites, we have to start breaking up our network into more and more areas. And the number of routers per area is going to depend on a couple of different factors. If the number of remote sites is low, we place the hub and the spokes within a single area. If we have multiple remote sites, we can make the hub an AVR and then split off the spokes to one or more areas themselves. Now, whether we put one spoke in an area or whether we put multiple spokes into an area is going to completely depend on the number of routers, the number of routes, the number of links, and so on that are facilitating a particular spoke site. Could also depend on the geography. Maybe all the routers on the left, area 2 here, are West Coast, and all the routers on the right, area 3, are East Coast. Who knows? And maybe area 0 is my data center in Dallas, right? All right. Now, the benefit of keeping each spoke in a separate area is that we contain branch routing changes and WAN link flapping from the core, but also from the other branches. The only downside is we're increasing the number of areas on the hub AVR, which then requires more processing capabilities and more power. All right. All right. So what we're seeing on this slide here is a table that kind of talks about the different advantages and disadvantages of using OSPF in a hub and spoke network. We actually have several different choices for the type of network that we decide that we want to use. For example, a single interface at the hub, meaning we're not using sub-interfaces, we're using a single physical interface at the hub. That gets treated as an OSPF broadcast or a non-broadcast multi-access network. Now, the benefit of that and the upside of that is that we don't have to have multiple subnets to connect all of the spoke routers. We're using a single IP subnet to connect to all of the spoke routers. That results in fewer host routes because we're still using a single subnet as our WAN, as opposed to having multiple sub-interfaces and then having to have a separate subnet for each sub-interface. Okay? The downside and the disadvantage is that we have to manually configure each spoke with the correct OSPF priority, because in a broadcast network, there's still a Rbdr election. All right? In fact, the only types of OSPF networks where there isn't a Rbdr election is when the OSPF network type is point to anything. So point to multipoint, point to point. We're not going to see a Rbdr election in those types of networks. All right. The other issue flashing in here. The other issue that we see with this particular design deployment model is that there's no reachability between the spokes, right? So we have a very labor-intensive layer 2 configuration. Everything has to go through the hub, and automatic neighbor discovery might not be automatic. We might actually have to define manual neighbor relationships, because in an NBMA network, which is non-broadcast multi-access, means that non-broadcast means no multicast. And neighbor discovery in OSPF is done through the use of OSPF hello packets, which are multicast in nature. All right? Now, if I decide to implement point-to-multipoint, a single interface in a hub using a sub-interface, you can't do point-to-multipoint without creating a sub-interface. But if I do point-to-multipoint, the configuration is very simple. The disadvantage of point-to-multipoint design is that additional host routes get added into the routing table because each link between the routers, the hub and the spoke routers, is a different subnet. So that means that for every spoke router, we're introducing an additional route into our routing table. The other problem is with OSPF network type point-to-multipoint, the timers are different. If you guys remember, what are the, well, let me ask you, just to make sure that we're staying engaged here. On point-to-point links and broadcast links, what are the default timers for OSPF? Anybody have any idea?
Remember something about 180 something was the whole time.
It's 10 and 40.
Oh,
right?
yeah. It was something 180. I forgot that completely.
Well, you're right, because on point-to-multipoint links, it's, well, it's not 180, but it's close, right? It's 30 and 120, right? Remember, the dead timer in OSPF is always 4 times the hello timer. Sorry, 40, let me think. Now I'm second guessing myself here. For Ethernet and point-to-point links, I know that the hello timer is 10 seconds, the dead timer is 40 seconds. And I believe, and I'll have to confirm this, I can't believe I can't remember this, but I've only taught it a million times, but on point-to-multipoint, it could be 60 seconds. No, it wouldn't be 60 seconds. It's got to be 30 seconds. Yeah, I believe it's 30 seconds. So 30-second hello timer and then 120-second dead timer, right? 4 times the 30 seconds. So I believe those are the timer values. I know for a fact that the 10 and 40 is correct. I'd have to verify the on the point-to-multipoint links, but I'm 99% sure it's 30 and 120. In any event, it poses a problem.
It was actually referring to BGP, keep alive. It was the whole timer, 180, 3 keep alives or 180 seconds.
Got it.
Yeah.
Yeah, it's kind of hard to keep all these different timers sorted out, right? I mean, EIGRP, it's 3 times, the dead timer is 3 times, and in OSPF, it's 4 times, and these values, of course, are configurable and whatnot. But anyway, the problem with OSPF, though, unlike EIGRP can dynamically adapt to different timers because they can negotiate the timer parameters during the hello exchange process. In OSPF, though, we can't do that. If the timers don't match in OSPF, we simply do not form an adjacency. All right? So the disadvantage of point-to-multipoint design is that those hello and dead timer intervals are longer. All right? Now, I will say this. Point-to-multipoint implementations are easier to configure compared to broadcast and MBMA. All right? They conserve IP address space compared to point-to-point because in point-to-multipoint, we still have a single subnet that we're using on the multipoint side as opposed to point-to-point for every single spoke. But we also reduce the need for Rbdr elections because there are no Rbdr elections on point to anything. Automatic neighbor discovery is assumed, meaning that we can use multicast to do our automatic neighbor discovery and so on. All right? Now, point-to-point, which is the one that's highlighted. Now, there might be a reason why it's highlighted. Well, it says at the bottom of the slide, use point-to-point with hub and spoke. All right. It takes a lot more work initially to do the configuration. Each sub-interface adds a route to the routing table. All right. Makes this option about equal to point-to-multipoint in terms of how the routing table is impacted by the number of routes. But after the configuration, point-to-point sub-interfaces provide the most stability. They're easier to manage, they're easier to verify and troubleshoot, and they work very, very well in a hub and spoke environment. All right? So in order of preference, I would say that the top one, the broadcast or MDMA modes, typically we avoid those as much as possible. They can be made to work, but it takes a lot of effort, and they generally lead to less stable network design. Or not so much less stable, but if there is a problem, the problem manifests itself in kind of mysterious ways. So it's more difficult to identify the issues in that type of environment. So the highlighted one is the one that we would typically stick with. All right? In some networks, the default reaction time of the routing protocol isn't fast enough. Right? We talked about this with EIGRP and the concept of trying to force a feasible successor by manipulating values to change reported distance and whatnot. So similarly, in OSPF, understanding what influences OSPF convergence will allow you as a network engineer and as a network architect and designer to improve the convergence process. All right? We already know generally what network convergence is. It's the time that's needed for the network to respond to whatever topology change event occurs. It's the time it takes for traffic to be rerouted to an alternate path when the primary path fails or when a more optimal path appears. Traffic that doesn't get rerouted or traffic isn't rerouted until the data plane data structures like our forwarding information base, adjacency tables and such have been adjusted to reflect the new state of the network. So in order for all of this to happen, all network devices have to go through 4 different steps. And this is the overall convergence process that we talk about. The first step makes sense. The first step, detect the event, right? We're looking at these 4 bullet points right here, right? What would be an event? A loss or addition of a link, a loss or an addition of a neighbor, etc., etc. Okay? Now this can be done through layer 1 techniques. It can be done through layer 2 techniques. We can use layer 3 detection mechanisms like carrier detection, routing protocol, hello timers, which we can adjust and fix based on our topology. BFD as well, which is what we talked about with EIGRP, is available with OSPF as well. So that's number 1. Let's make sure that we know that an event occurred. Number 2, propagate that event, right? Routing protocol update mechanisms are used to forward information about topology changes from one neighbor to the other. The propagation of that information, how long it takes for a triggered update to be sent and then to be repropagated, is very important. Now, there isn't a whole lot that we can do with regard to increasing the speed of event propagation. But there are efficiencies that we can add to either prevent propagation from occurring through the use of things like summarization, route aggregation, and so on, or there are options that allow us to ensure that information is efficiently spread through the use of things like a designated router or a backup designated router and so on. All right? All right. And we'll talk about that as we move. Once the event gets propagated, the next step is to process the event. The information needs to be entered into the data structures, and data structures in the case of routing protocols include things like topology tables, routing tables, in some cases neighbor tables. Those are generally the three data structures that we talk about when we talk about BGP and ISIS and EIGRP and OSPF. Okay? Once the event is propagated, we start the processing by running the routing algorithm. The routing algorithm needs to be invoked to calculate updated best paths or to calculate our new topology. And then finally, the last step. Remember I said there were 4 steps. We see them listed on the slide. The last step is to update forwarding data structures. So the routing algorithm runs its calculations, and as a result, that information needs to be entered into our data plane packet forwarding data structures, namely our Cisco Express forwarding data structures, right? Only after all 4 of these things have occurred has the network converged. So as you're analyzing your network design and as you're implementing your OSPF network design, the first step is extremely dependent on the type of failure. Is it a layer 1 failure? Is it a layer 2 failure? Is it a layer 3 failure? And what combination of tools do I have in place to detect those various failures? So the first step may or may not be directly related to OSPF, right? It may be related to frame relay, it may be related to MPLS, or some other protocol, right? The second and third steps are really more specific to OSPF. And the way that we affect those steps is we tune associated parameters to improve OSPF convergence time. All right? And then the last step, we really don't have a lot of control over as well. It's not routing protocol specific. It's going to depend on the hardware platform, mechanisms involved in programming those data plane structures that have to be reprogrammed. So that's a lot to do with the CPUs, the distribution, the distributed platform architecture, and so on. All right. In network environments where routing and routers running OSPF have to detect network changes quickly, you have to rely on external protocols like BFD, bidirectional forwarding detection. Again, this gets us from second convergence times, 10 seconds, 50 seconds, 30 seconds, whatever it is, down to a sub-second timer. All right? The BFD is not a protocol-specific function, right? It's not specific to EIGRP. It's not specific to OSPF. It doesn't transport its information inside of EIGRP datagrams or OSPF datagrams. We already talked about how it transports information inside of UDP in a separate data stream, a unicast data stream, all right? But one of the most significant factors in routing protocol convergence is the ability to detect and respond to link or node failures. All right? Remember, we talked about, well, briefly, the functions of BFD. BFD is a technology that uses something called fast layer 2 link hellos to detect either a completely failed link or even links that are operating unidirectionally, one way. Okay? And somewhere between 50 milliseconds and 150 milliseconds, we see this event detection. Okay? Very, very important. Now you might say, well, you know, that's great. I want to implement BFD, but the problem with implementing BFD is that it's just adding another layer of complexity on top of my configuration. It's adding more CPU cycles, more processing on top of my configuration. That may be somewhat true. However, the CPU impact of BFD and the impact of using BFD is far less significant, particularly on the CPU, than the impact of maybe speeding up your routing protocol hellos. And the reason why is because BFD processes are shifted to the data plane rather than the control plane. Hello packets are sent up to the control plane, and routing protocol processing is sent up to the control plane rather than the data plane. All right. Cisco did a test, and I read this recently, actually, on non-distributed platforms. In other words, where you have central processor, central processing engine, single data plane, single control plane. There was about a 2% CPU increase above baseline when I have 100 concurrent BFD sessions. So relatively benign process. All right? Very benign process. Okay? Have you guys seen, I know you guys make use of this, have you guys seen any kind of impact beyond that on your platforms? How many BFD peers are you guys configuring in your network? Anybody? Nobody? Okay. I imagine that it falls below this threshold, right? Because I don't think that you guys are supporting 100 concurrent BFD sessions. I wouldn't think so. My guess, based on what you described, is you only have a couple, right? And certainly when you only have a couple, then...
Yeah, that's true. I only have a couple. It looks like I'm muted all over the place.
That's okay. Remember, BFD is a completely independent protocol, all right? When you configure it, you have to tie it to the selected routing protocol, all right? In OSPF, you can configure BFD to support OSPF globally under the routing protocol configuration, or you can actually configure BFD on a specific interface, okay? All right. Another concept that we don't concern ourselves with so much in EIGRP because of the nature of the databases and the nature of propagation of information in EIGRP is how the network convergence requires all affected routers to process a particular network event. Now we have the ability to optimize the protocol behavior and improve convergence time if we have a good understanding of OSPF event propagation. All right? And I'm going to slow it down a little bit here and talk about this because this is one aspect of OSPF that a lot of people are not aware exists. And it is, from a design perspective, is definitely one of those things that you want to be familiar with. All right? We know that OSPF topology changes are advertised by flooding link state advertisements. All right? Propagation delay, not processing delay, not serialization delay, but propagation delay equals I guess the sum of various other types of delays. So let's think about what it takes to propagate LSAs. You've got your generation delay. How long does it take for the router to actually generate an LSA? Number one. You've got your LSA arrival delay. How long does it take to actually get to its destination? And then you've got processing delay. Now, a lot of times when people think of propagation delay, they think of when the data gets onto the wire, how long does it take to get from one side of the wire to the other? But in the concept of OSPF, propagation delay is, specifically related to OSPF, is the sum of those other delays: LSA generation delay, LSA arrival delay, and LSA processing delay. Okay? Now, the original OSPF specification required that the generation of similar LSAs, that means that they have the same link state ID, the same link state type, origin router ID, etc. They might have different updated content, but those similar LSAs need to be delayed for a fixed interval amount. And in OSPF, in the original specification of OSPF, that defaulted amount was 1 second. Now that seems pretty significant, right? Because we are talking about propagating changes, but they're just changes related to an already existing entry in my database. All right? So Cisco decided that they were going to try to optimize this behavior. And they did that by implementing an exponential backoff algorithm. And what that exponential backoff algorithm does is it dynamically calculates the delay before it generates this similar LSA. Remember, a similar LSA is link state ID, LSA type, origin ID, just maybe different content. Maybe a metric has changed, maybe a specific value of the actual route has changed, whatever that might be. Now, the backoff timers are initially set to a low value. And they're set to a low value so that we can establish quicker convergence times. However, if successive events get generated for the exact same LSA, then the backoff timer starts to increase, because now we're starting to affect the production of the network by generating too many LSAs for the same information. Now, this is the part that gets a little confusing. You know, we see on the slide here, they have these 3 intervals that they talk about, 3 configurable parameters: the start interval, the hold interval, and the max interval. The descriptions here aren't that great, so I'm going to try and expand on them a little bit to try and make it easier to understand. All right? The start interval. This value defines the initial delay that's used to generate the LSA. And remember, that is a variable value, right? Before it was always 1 second, but because of the backoff algorithm that's dynamically calculated, that delay changes depending on how many similar LSAs I've already sent. All right? Now, the initial value is still configurable, and that can be set to a very low value. In fact, it wouldn't be a second. It might be as low as 1 millisecond or even 0 milliseconds. All right? The default is actually now 0 milliseconds, which means it's basically like a triggered update. As soon as the update occurs, send it out. All right? Obviously, the benefit of having a low value on this timer improves convergence time, because those initial LSAs for whatever new event is being generated, those get generated as quickly as possible and get sent out. So the LSA generation delay, that's part of this propagation delay, the LSA generation delay is short, right? I mean, it's practically non-existent, 0 milliseconds. All right? Now that will adjust. Remember, we've got that backoff algorithm that will increase if we're constantly sending updates based on the similar LSAs being sent multiple times. Okay? But I think you guys understand that the concept of the start interval. It's just that time that's established for sending out that initial LSA. All right? Now the hold interval. This is the minimum time. All right? It says on the slide it defines the wait time between subsequent LSAs. Its value doubles for each consecutive packet. Kind of makes sense, right? But let me see if I can kind of describe it in a little bit more detail. I would define it as the minimum time that has to elapse before the flooding of an update instance of an LSA. Now, flooding means resending the LSA. All right? It's an incremental value. Initially, the hold time between successive LSAs, just like they described on the slide, is equal to whatever the configured value is. The default happens to be 5,000 milliseconds. So at a minimum, I've got my start interval of 0 milliseconds. I've got a hold interval of 5,000 milliseconds. All right? Okay? Hold on one second. Just checking something real quick. I was trying to see if it was, I'm pretty sure it's 5,000 milliseconds, but I want to make sure I'm giving you guys the correct information here. All right. Yes, it is 5,000 milliseconds. Now that is a configurable value. All right. And that initial configured value is 5,000 milliseconds. So each time a new version of an LSA is generated, that hold time between the LSA is doubled until we reach the max interval. All right, which we haven't talked about the max interval yet. All right. And then basically what happens is once I've reached the max interval, I just keep repropagating LSAs at that maximum time value. All right? Which brings us to the third and final configurable parameter, max interval. This is going to define the maximum amount of time that can elapse before the flooding of an updated instance, I guess, for lack of a better term, of an LSA gets sent out. So this is that exponential back-off timer value that gets reached. So let's say, for example, I've set my max interval to 10,000 milliseconds. I know my hold interval is 5,000 milliseconds, and I know my start interval is 0 milliseconds. My initial LSA, generated LSA gets sent out at 0 milliseconds. The minimum amount of time that has to elapse before I send out the next LSA regarding the same information is 5,000 milliseconds. The back-off algorithm says double it each time, whatever the hold interval is. So I'm going to double it to 10,000 milliseconds for the next. So the next propagation, flooding, update, instance, whatever you call it, gets sent out at 10,000 milliseconds. And because that is the max interval value, every 10,000 milliseconds, I'm sending out that I'm propagating or repropagating or flooding that LSA. Okay? We never exceed the maximum interval value, basically. Now, what are the defaults? For the start interval, the default is 0 milliseconds. For the hold interval, it's 5,000 milliseconds. For the max interval, it's 5,000 milliseconds. Okay? Which means that I'm going to be flooding LSAs every 5,000 milliseconds. All right? Now, keep in mind, we are not talking about the paranoid update. We are not talking about repropagating the same advertisement. we're talking about propagating changes to an advertisement. Similar LSAs, but slightly different content. All right, we don't do this if the content is the same. We simply do our paranoid update every 30 minutes. So this would only occur if something within the LSA changed. The link ID is the same, the LSA type is the same, the origin router ID is the same, but the content is slightly different. All right? I know that's a lot of information. Hopefully, you guys understand that concept. All right? Now, what you decide to set as an optimal value depends on the network itself. If you tune these timers too aggressively, you're going to get excessive CPU load during the reconvergence process. All right? Especially if the network is unstable for a period of time. And by the way, that instability could be catastrophic because it could lead, if you have really aggressive timers, it could lead to even more instability because of links being congested or CPU cycles being overutilized, so information is being dropped, hello packets are not being processed, et cetera, et cetera. All right? If you lower the values too much, then convergence degrades, right? It takes too long for the network to converge or handle topology changes. So it is really a balancing act, right? What I generally recommend, although I have to say I've really never changed these values, I've never seen a need to change the default values, but if you do find a need to change those default values, lower the values gradually from their defaults. Observe the router behavior. Determine what the optimal value is for your network based on the stability of your layer 1 links, your layer 2 links, etc. All right? When you adjust the throttle timers, the link state advertisement throttle timers, you may also have to adjust the arrival timers. All right? Because anytime LSAs get received at a higher rate than the value of the arrival timer, those LSAs actually get discarded. So you're then wasting network bandwidth and network resources propagating LSAs that aren't going to be processed. So if you want to prevent routers from dropping valid LSAs, make sure that the LSA arrival timer is configured to be lower. I usually make it lower or equal to the hold interval timer. Okay? We didn't actually talk about how to adjust the timers in the command line. Hopefully, I'll be able to show you that a little bit later on. All right? Okay. So, here is a pretty little slide that kind of depicts, well, the whole scenario, right? In this particular diagram, the OSPF exponential backoff algorithm is depicted, right? We assume that every second an event happens that causes some sort of new LSA to be generated. Now, with the default timers, we talked about this, with the default timers, that initial LSA will be generated after 0 milliseconds, and then there will be a 5-second wait until we see our successive LSAs. Those are our default timers, right? So think about the process here. This top box here, or top graph, represents actual events that are occurring. Now, hopefully, you fix that problem, right? You don't want changes in the network every second. But for the purpose of demonstrating this concept visually, we're assuming that that's occurring. This is the default generation timer. Now, our start timer is right here, 0 milliseconds. But then remember, our default hold interval is 5,000 milliseconds or 5 seconds. So every 5,000 milliseconds, whoops, sorry about that. Every 5,000 milliseconds, because that is also our configurable max interval, right, is 5,000 milliseconds. We're sending out we're propagating these events, okay? Now, with the default timers, again, that initial LSA gets generated after 0 milliseconds. Now, if I set the LSA throttle timers at 10 milliseconds for my start interval, 500 milliseconds for my hold interval, and 5,000 milliseconds for my max interval, that's when we see the bottom slide, the bottom tuned timers graph. All right? Here's our initial propagation, which is 10 milliseconds. Here's our second propagation, because that is my hold interval, 500 milliseconds. Remember, my max was set at what? What was my max set to? 5,000. Max weight is 5,000. So I'm going to double this hold value up to the point where I get to 5,000. Obviously, I can't double 4,000 because that would put me at 8,000, right? But I can double 500 to 1,000. I can double 1,000 to 2,000. I can double 2,000 to 4,000. All right? And then from that point forward, what happens? On a 5,000 millisecond wait time, every 5,000 milliseconds we'll apply that value to our successive LSAs from that point forward. Now, once the network stabilizes, here's a very important concept. Once the network stabilizes and the LSAs stop getting propagated, we reset everything back down to its initial values. So we're going to go back down to 10 milliseconds for our start time. We're going to go back down to 500 milliseconds for our hold interval, and we'll go back up to 5,000 for our max interval. All right? Keep in mind, guys, that these changes, these topology changes, shouldn't really be occurring in your network, right? You shouldn't be seeing changes happen constantly in your OSPF network. If you're seeing stuff like that, you really should consider maybe looking at what the reason for that is, as opposed to adjusting these timer values. All right? All right. The timing of successive OSPF calculations, algorithms, shortest path first calculations, is throttled pretty much the same way that LSAs are throttled. We use an exponential backoff algorithm, and then we repeat those SPF, any SPF recalculations causes the hold and the max weight and so on. All right, so what we're talking about now is not event propagation. We're talking about event processing. How often am I going to run Dijkstra's algorithm based on new advertisements I'm receiving on the router? So this is at the receiving side, not the sending side. Remember, we talked about synchronizing this information, making sure that the sending timers, the LSA propagation timers, get synchronized with the OSPF event processing timers. All right, so once a router receives an updated LSA, it needs to schedule the Dijkstra's algorithm to process that update. We have to go through the shortest path first calculation. All right, now, topology changes aren't usually going to affect just one router. It's going to affect lots and lots of routers. All right, so it actually might benefit you. It might, well, as Bush would say, be prudent, right? He said it wouldn't be prudent, but I'm saying it might be prudent to wait a little bit of time for more updated LSAs to arrive and then to only run the shortest path first algorithm after that waiting period has expired, just to make sure that you're receiving the latest information. It's very similar to like a hold down timer that you would see in RIP, for example, right? Now, it's much more efficient than RIP. RIP is not very efficient at all, but all right. This action, this idea of waiting allows SPF to process multiple updates in a single batch, I guess, right? Single run. If your topology is constantly changing because of a repetitive fault, maybe a flapping link or faulty connectors or whatever, running the SPF algorithm over and over again would really just be useless and wasted resources, right? You really wouldn't need to do that on the router because that event is occurring over and over again. All right? So if a router keeps receiving those updated LSAs, that delay that we can configure before we run the SPF algorithm probably needs to progressively grow or somehow dynamically change to prevent or reduce the negative impact because of a flapping network or a flapping interface or whatever it might be that's constantly changing in the topology. All right? So we have three timers, three tunable timers, and we see them on the slide here. Three tunable timers that are used for this particular process. All right? The timers that are specifically involved in OSPF, well, you can see from the names, they're very similar to the LSA propagation timers, right? The SPF start timer. That's the initial delay to schedule the algorithm calculation after a topology change has been identified. The hold timer, the minimum hold time between two consecutive SPF calculations. It's an incremental value that is exponentially backed off, just like we saw the hold timer with our LSA propagation. So if it's 5,000 milliseconds, then I'll do my initial calculation, I'll wait 5,000 milliseconds, I'll double it to 10,000 milliseconds, I'll triple it to 15,000 milliseconds, all the way up to the SPF max wait period. All right? So they can be the same values, the hold and the max wait, or they can be configured different values, but the hold is always less than the max wait. Now, by default, we talked about the defaults for LSA propagation, 0 milliseconds, 5,000 milliseconds, and 5,000 milliseconds for each respective value. In this particular case, Cisco routers schedule the SPF algorithm to run every 5 seconds after it receives an update. If an updated LSA arrives after the algorithm is run, then the subsequent delay grows up to 10 seconds. All right? You can see already that is similar, but not exactly what we saw with the LSA propagation timers, what we call the Lsa Throttling Timers. 5 seconds is the same, right? For a SPF hold timer, 5 seconds is the same. 5 seconds is 5,000 milliseconds. I don't know why they define it as 5 seconds. Why not define it as 5,000 milliseconds? That's what it is in the Lsa Throttling timers, but it's the same value. However, the max wait time, which is 10,000 milliseconds or 10 seconds respectively, is different, right? The max wait time in our Lsa Throttling timers is 5,000 milliseconds. So I would highly consider, as part of the implementation process, to adjust those timers to be similar, right? The other thing that you need to consider too, and this is something that a lot of people forget, is you need to consider the time it actually takes for an SPF calculation to complete. And that's totally based on the size of the databases, the number of topology changes, the CPU ability of the router, the memory of the router, etc. All right? Obviously, there's no way to run a second SPF algorithm or calculation if the previous calculation hasn't completed yet. All right? Always make sure that the SPF hold timer is higher than the time it takes to run a complete SPF. Also consider future network growth. The amount of time it takes to calculate or run an SPF calculation now might be shorter than it will be in 6 months from now when you add additional networks to your topology. All right? All right. Cruising right along here. By design, and I've mentioned this a couple of times already, OSPF floods or refreshes link state advertisements or its database every 1800 seconds. Okay? Now, all LSAs expire if I don't receive an update or a refresh. All LSAs expire in how much time? 3,600 seconds, right? 1,800 seconds is 30 minutes, by the way. 3,600 seconds is an hour. So if I don't receive updated information or the same information about an LSA within 3,600 second period, I'm going to assume that LSA is no longer valid. And I'm going to flush it from the database. Now, we always talk about the inherent intelligence that link state protocols bring to the network, like triggered updates, only sending out the changes, only sending out updates when they're necessary or when something changes. So this periodic refresh of LSAs really kind of introduces unnecessary overhead in a network that is very large and very stable. Okay? So we can use something called the OSPF flood reduction feature, flooding reduction feature, flood reduction feature, to reduce this unnecessary refreshing or flooding of an already known and unchanged link state advertisement. All right? Now, this is defined in RFC 4136. Yeah, it's listed on the slide there. 4136. I can never remember all my RFC numbers, but it's helpful when it's on the slide. That way I know I'm not giving you guys bad information. But RFC 4136. And in that RFC, it states that an interface that's configured with flood reduction advertises LSAs with the bit, there's a bit that's set called the do not age bit. And you will see this in the actual database. All right? When an LSA has the do not age bit set, that LSA does not need to be refreshed unless there's actually a change to that particular advertisement. All right? Obviously, if the network is stable and the network topology doesn't change and the routers are good to go and interfaces aren't going up and down and metrics aren't changing, this would be a pretty simple thing to consider. To me, though, isn't it really something that should always be considered? Because if the link state advertisements don't age, the only effect, negative impact on your network that you would have is if networks go stale, right? Because if a network goes down, you should get an update. if a metric for a network changes, you should get an update. So having this do not age bit set in the link state advertisement is actually a pretty good deal. All right. The downside to the configuration, and I've implemented this configuration many, many times, is that you can only implement OSPF flood reduction on a per interface basis. All right. Now that's actually good and bad, right? It's bad because then you have to go enable it on every stinking OSPF interface that you want the feature enabled on. But it's actually good because that you implement it on a per interface basis as opposed to in the global routing process, because some interfaces or networks behind specific interfaces might change more often, or there might be more of a likelihood that information gets stale. So we would not enable this RFC 4136 flood reduction feature on those interfaces, and then we would enable the feature on the interfaces that are more stable, right? Now, what was the whole point of even having this flood feature? Like I said, it doesn't really help us when topology changes occur, because when topology changes occur, we get LSA updates anyway, right? Or link state advertisements anyway. The whole point of this feature is to ensure that we can recover from bugs, glitches in the software, and so on. And that's what they list on the slide there. And that's really the main purpose and the main reason. Okay? All right. The other and the last feature that we'll talk about, all right, is another feature that's part of OSPF. It's not enabled by default, but it is a feature that in a larger OSPF environment you might want to consider running, is the link state database overload protection feature. Okay? The LSDB overload protection feature allows you as an administrator to limit the number of non-self-generated LSAs to protect the OSPF process. Okay? Now, what the heck does that mean? A non-self-generated LSA is an LSA that you're receiving from other routers. Maybe somebody puts a rogue router into your network and starts generating or flooding LSAs into the network to perform some sort of denial of service attack on your routers. Well, it's almost like a rate limiting feature for those LSAs that are being received. All right? Because every time I'm receiving those excessive LSAs that are generated by other routers in the OSPF domain, I'm draining my CPU resources, I'm draining my memory resources on my local router. All right? So it's almost like a control plane protection feature. You know, we talk about in the CCNP network foundation protection, NFP, right? And in NFP, we're trying to protect the control plane functions and management plane functions of the router against denial of service attacks, against misuse or misappropriation of resources on the router, and so on. This is a similar feature, but it only applies to OSPF, obviously. All right? When you have other routers in the other OSPF routers in the network, maybe they're misconfigured, maybe it's intentional, maybe it's not intentional, whatever. But the end result is they're generating a high volume of link state advertisements. This protection mechanism prevents routers from receiving too many LSAs, which would result in high CPU utilization and memory resource issues. Okay? When the OSPF link state database overload protection feature is enabled, the router keeps a count of the number of LSAs that it's received from and this is done on a per interface basis as well, but overall, when that threshold is met, when we reach that threshold for the number of LSAs, a syslog message gets generated, okay? When the configured maximum number of LSAs gets exceeded, the router sends a notification message. All right, so initially we don't block the LSAs. Initially we don't take a sledgehammer and destroy those other routers, right? But if it's persistent, and in the case of persistent, that configured maximum value has being met or exceeded for 1 minute, then the router takes down all of its adjacencies, it clears out its OSPF database, and refreshes the OSPF process. Now that seems pretty drastic, right? Because it's kind of like you're trying to prevent a denial of service attack by initiating a denial of service attack on yourself, right? There are other ways that we can configure this process. There is a state called the ignore state, where all OSPF packets received on the interface that belongs to the OSPF process get ignored. No OSPF process packets get processed or generated for any of those interfaces that are participating in that process ID. And we stay in that ignore state for a configured amount of time. All right? And that ignore time is actually configured using something called the max LSA command. All right? We don't see the specific command structure here. Again, as I mentioned, I'll try to put together some EIGRP exercises and some OSPF exercises where we can see some of these configurations a little bit later on, time permitting, of course. Okay? Each time the OSPF process gets into this ignore state, a specific counter gets incremented. If that counter exceeds the number of counts that are configured by the ignore count keyword, which is another configurable value, all of these values are configurable in the OSPF process, then we stay permanently in that same ignore state, and the only way to get out of that ignore state is through manual intervention. All right? Now there's another timer value called the reset time, and we use the reset time command to set that value. If I stay in what we call, quote unquote, the normal state of operation for that reset time period, then I'm going to reset the ignore state counter to 0, and I'll start processing packets normally again. Something to be very, very careful with, because if you set your thresholds too low, you may end up causing more problems and more issues in your OSPF domain than if you were to simply allow the flooding of LSAs to occur and maybe have your CPU operating at a high duty cycle for a certain period of time, right? It is, again, these are thresholds that you have to tune, you have to monitor, and you have to see what is acceptable for your particular environment. Cisco doesn't actually have specific recommendations for these values. Now, I will say, in my experience, because we're running things like authentication and we're running a secure routed environment, I don't typically concern myself too much with this overload protection feature. And I'm assuming that none of you guys have implemented that feature in your environments either, but maybe something to consider. I would only consider doing it if you run into a situation where you see a router causing this problem and you want to ensure protection against that in the future. Okay? All righty. So OSPF scalability is influenced by the stability of the connections, the number of prefixes or routes, the number of adjacent neighbors, the number of routers in an area, the number of areas supported by an ABR, et cetera, et cetera. Pretty much all the same thing we talked about with the IGRP. The only difference is, in this case, we're dealing with areas and ABRs and ASBRs. Keep it simple. Keep it as stubby. Keep it summarized, right? Those are the three kind of basic design elements of OSPF, right? Place the area border routers so that you maintain a stable backbone. And divide complexity from complexity. In other words, take your more complex implementations and segregate them and segment them into their own unique areas. All right? Use mesh groups technique. Now, we, again, can't do mesh groups specifically in OSPF, but we can simulate mesh groups by identifying where LSAs can be flooded to. Balance between the number of areas on the ABR, the WAN link stability, positions, position the ABRs in your hub and spoke network and so on. Adjust your timers and protect OSPF routers from flooding and database overload by using the protection mechanisms that we just previously talked about. Okay? So that concludes our OSPF lesson. Tomorrow, we are going to get into BGP, which is a very long, well, it's its own module, basically. So several different chapters on BGP that we'll get into tomorrow. All right.